Unveiling advanced hybrid emulation methodology for accelerated hybrid home screen bring up and system level verification. Abstract. SoC software bring up and its validation are usually done at post-silicon stage, which can affect the time to market the product and the cost of silicon spin. It is also difficult to debug hardware-software design bugs at post-silicon level because of less RTL design visibility. So early software bring-up and validation is very crucial. Therefore, the platform teams needs a high-speed model of the SoC months ahead of silicon availability to design software bring-up and application driver development. Because of less emulated driver clock frequency, software bring-up cannot be done in FPGA-based emulation verification environment. Therefore, platform teams need a high-speed model of the SoC month ahead of silicon availability to begin software bring-up and application driver development. To overcome less emulator speed and to accelerate software development, hybrid emulation is developed. Hybrid emulation combines virtual prototyping and hardware emulation. To speed up the hybrid emulation, some components of SoC move from emulator to virtual side. So in hybrid emulation, one part of SoC design runs at emulator and other part of the design run in virtual platform. So virtual prototype are high performance SystemC models of a particular IP, block, or entire SoC. These are modeling the behavior and inter-block communication at transaction level, TLM, which makes these faster than equivalent cycle accurate RTL. Introduction. In today's competitive era, time to market a product is very important. SoCs are becoming increasingly complex, so early software development and verification is very crucial. Design teams cannot afford mistakes when making critical architectural decisions affecting performance or other requirements early in the development processes. SoC software bring up its validation are usually done at the post-silicon stage, and which can affect time to market a product or cost of silicon respin. It's also difficult to debug hardware-software design bugs at a post-silicon level because of less RTL design visibility. Therefore, software teams need a high-speed model of the SoC months ahead of silicon availability to begin application development. So it is viable to develop this software month early at pre-silicon. With the increasing complexity of SoC, the validation phase now has been more important during the development. The risk of shipping buggy SoC must be minimized through the careful analysis and the use of different verification and validation processes, starting from the very beginning of the project and continuing through each design phase until the end of the life cycle of the chip. The design of SoC is usually just a small part of the job comparing the entire effort to accelerate development of new product. The majority of the costs are in the verification of the product and developing the software to run on it. The following chart shows the analysis of the cost involved in various SoC validation platforms with respect to increase of the design complexity. Figure 1 is a system SoC, system on chip SoC development stages and their cost comparison based on a scaling transistor size. The chart shows the growth of the cost associated with the validation of software have been growing exponentially when compared to with the process technology scale. This is the reason why we both see a dramatic rise in importance not only at the end of the design phase but from the beginning of the project, where the hardware design verification and software are performed simultaneously. Chapter 2. High-performance emulation methodology, need impact. There are mainly 4 methods to test the design before tape-out of chip. Each of them has different advantages, disadvantages. Thus, all 4 are used during the development of SoC. Table 1. Comparison of different verification platforms with respect to a various aspect. Simulator. Simulator is used for the very beginning of the design because it gives a complete view of the signal in the RTL and is often used to verify functionality at module level. When the structure of the chip is close to being completed, the limit of this method starts to rise quickly. The huge computational power required to the simulation limit the speed of the execution of 100 Hz for the latest cores, requiring too much time to execute a boot of an operating system, for example. Emulation. The performance problem could be partially solved by using an emulator, which with a specialized hardware can reach a speed of 5 MHz ZeBu Server 5, still keeping the same complete view of the internal status of the system. The main disadvantages of emulators are cost of ownership, which is order of magnitude bigger than the other method, and again the time required to boot an actual operating system is not suitable for software developer who needs to the system reboot a few times during the design day and when developing kernel and device drivers. FPGA. Software developed and validation could be done at FPGA prototyping boards, but because of the high cost and less debug visibility, it's also not preferable for it. Silicon. Usually, software development and validation happens at a post-silicon stage. As increasing the SoC complexity and short schedule time, software development is also becoming time-consuming, and it's very challenging to complete it on time. Also, less RTL debug visibility of silicon. It is difficult to debug and identify type of the bugs. Either they are hardware bug or software bug. So to avoid time risk and silicon risk being cost, it is better to start software development and validation on pure silicon stage. Therefore, we can avoid the risk. A. Challenges to bring up software in pure emulation. Software development can be done using pure emulation, but achieved emulator driver clock frequency is too less to bring up the Linux kernel. Android OS to develop the system-level drivers for various complex IPs. It takes around 4 days time to bring up the complete Android home screen on emulator, whereas the design is running at a 1 MHz driver clock. So performing the software development iteration on pure emulation is no more realistic. Figure 2. Full Android 13 boot time on emulator. To overcome the last emulator and accelerate software development, hybrid emulation is developed. And Figure 3 shows the hybrid emulation sits in between FPGA and silicon with respect to a debug to visibility and performance. So hybrid emulation has better performance to emulation and FPGA. It all helps the easier platform on gradability and debug software bring up due to the better RTL design debug visibility compared to a post-silicon. Furthermore, because of the full design visibility of the hybrid emulation, it significantly helps the user to debug any hardware and software issues and verify the corresponding fixes against the accurate virtual model with a quick turnaround time. Hybrid emulation supports all emulator debug features, along with the software debugger like waveform dump, 1232, TLM debugger, transactor, and adapter debugger through the log level. The Figure 3 is hybrid emulation debug visibility versus performance. Third, Chapter 3 is hybrid emulation introduction. Hybrid emulation combines virtual prototyping and hardware emulation. Hybrid emulation is done when a part of the design runs on an emulator and other part runs in the virtual prototype. Hybrid platform has two domains: virtual platform side TLM and VDK, emulation side RTL, VDK, CPU, GIC, MCT, UART, Parry, storage, DRAM, bus, memory controller, IPs, and others. The virtual prototype component. The virtual prototype component are high performance and SystemC models of the entire SoC, a particular block or a system model. They have primarily been used by project architects to estimate the SoC power, performance, and for early software development. Architects will use them for architectural design optimization and to check that the designs meet certain goals, such as performance and/or power. Architects may also use virtual prototype to assess the correctness of the house bus architecture. The hardware emulation component. An emulator runs much faster than a software-based RTL simulator has simulation-like use models. All the debug features available in simulation are present in a simulation. The user can add dump bars and assertion monitors and more. Emulator makes it possible to bring up a full SoC design before even an FPGA-based prototype is available. The design team can begin hardware-software integration. The RTL probably is not stable at this stage, and that's why the full debug capability of the hardware emulator is so important. Chapter 4. Development of the hybrid platform. Hybrid emulation enables SoC development teams to take full advantage of their investment in a high-performance emulator across their entire project to meet the increasing software verification and competitive challenges. Typically, a model of the processor is run in a virtual platform, and then a last of RTL design runs on the emulator. The task of a virtual platform is to have just the emulator accuracy to support the level of software being run on it. This is achieved by modeling the behavior and inter-block communication at the transition level, which makes these faster than equivalent cycle accurate hardware. If a user has necessary models or libraries of models, usually retaining SystemC, then the user can create a virtual platform for any SoC. Such libraries of the SystemC models are available as open source or commercial packages, such as a system-level library. Usually, ARM IP dominate SoC designs, so you will need models of the ARM cores and the bus system models. ARM supplies such models by the name of the fast models, and these models are already in wide use in the virtual platform. Partitioning an SoC across the virtual and hardware platforms. In hybrid emulation, there will be some blocks of the SoC design running FPGA hardware and the rest in the virtual models. In some cases, the choice will be governed by the availability of models or RTL. If you have both, however, it will depend on the side of virtual hardware boundaries where the particular block is placed. This leads to critical question of where to place a boundary between virtual and physical domains. In pure emulation model, there are many transactions between CPU and DRAM. This is a bottleneck for Android Linux booting and software development. To overcome this, CPU and related components are moved to virtual side, software side, for OS boot and run acceleration in hybrid platform. This acceleration is achieved in hybrid because of virtual models of the CPU launch instruction set simulator ISS to perform much faster compared to CPU gate level behavior in emulator. Hybrid emulation has a fast model of the DRAM instead of RTL memory model. Hybrid fast memory is shared memory between virtualizer and emulator, which is properly synced between them. The figure 5 is partitioning an SoC across a virtual and hardware platform. B. Hybrid platform architecture. Figure 6 shows hybrid platform architecture on ZeBu 5 server. To connect virtual component to the hardware on emulator various adapter and transistor are getting used. Adapters are integrated virtualizer studio, and these are used to connect a virtual component to the hardware through different transistor implemented in emulation test bench. jar 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 is ZeBu hybrid adapters library which provide a wrapper of all required adapters. These wrappers can be used inside the virtualizer as TLM models. Figure 6 is hybrid platform architecture. As discussed above, while booting the Linux kernel, most of the transition happens between CPU and DRAM. To reduce CPU to DRAM memory access latency, shared DRAM memory is developed in a hybrid platform. In shared memory, we have DRAM, GRAM memory on emulator and shadow memory at a virtual side, which are properly synced through the transistor to minimize software virtual and emulator transaction. Figure 7 is shared DRAM model in hybrid emulation. Debugging method. In any validation platform, supported debugging methods are very important. Hybrid emulation supports various software and hardware debugging methods to debug any encountered bugs while developing software. Below are few debugging ways to which hybrid emulation support. 1. The TLM transaction debugging through chart view. 2. Software debugger through VP disassembly feature and traceability debugger. Transistor and 3. Transistor and adapter debug through a different log levels support. 4. Hardware debug through the waveform dump in Verdi. First two debugging methods usually used to debug software bugs by booting, breakpoint, bypassing function, forcing the register, and dumping the memory through the traceability debugger. Third debugging method is used to debugging transition between the software and hardware through the various adapters supported in logo levels. Fourth method is used to debug RTL functional behavior through the behavior dump in Verdi. D. Challenges and limitation. One challenge with a hybrid emulation approach is that can generate an insane amount of the data very fast. As a result, there is often a window of millions of source cycles that are recorded and can be used when a bug is encountered in the root cause. However, running software and emulation and doing a system boot or bring up a software may take billions of instructions. The point at which the bug was injected by an unexpected behavior at the point in which it is first observed may be too far apart the million cycle windows to be useful. Therefore, it's a little bit difficult to debug software bugs and SystemC models, while the pure ZeBu software debugging is easy because the whole SoC runs on hardware. Hybrid emulation has some limitation. As in hybrid emulation, we use SystemC and TLM models of some SoC components, which does not support cache coherency. So while software developed through the hybrid emulation, we need to disable cache coherency. One more limitation ARM-fast models has, it does not support multi-core simulation, so we also need to disable SMP while developing Linux kernel or Android home screen. Chapter 5 Result and Benefit. Pure emulation versus hybrid emulation. Software bring up the shows in table 2 taken from our complex Exynos SoC, which has almost 2 billion of gate. At table 2 shows, in simulation, software developed is unrealistic because of less runtime performance. In emulation platform, take almost 4 days to bring up the full Android home screen. Therefore, pure emulation platform is also not preferred to bring up the software where we need to run many iterations while developing software and drivers. Hybrid emulation takes almost 2 minutes to boot Linux kernel, 12 minutes to get an Android logo, and a total 72 minutes brought up an Android home screen on display panel. Table 2, software bring up time to comparison in various platforms. Figure 7, snapshot of Android logo and a home screen and display panel. The Chapter 6, Future Scope. A. Enabling CPU benchmarks. In hybrid emulation to enhance performance with black box real RTL CPU from emulator and integrated ARM, the ARM releases SystemC, fast model of corresponding CPU at virtual side, so it is not possible to perform any CPU benchmarking in hybrid emulation. So we are trying to enable perform CPU benchmarks in hybrid emulation through gear shift methodology. And this methodology, once Linux Android is brought up with a virtual side CPU SystemC CPU model, and then left shift or CPU state from virtual CPU to RTL CPU, as Linux Android already booted up, CPU benchmark can be run with a real RTL CPU on emulator. Figure 7, gear shift methodology in hybrid emulation to perform CPU benchmark. C. Vertical support enablement in hybrid emulation. As we mentioned section 5, D. In hybrid emulation challenges, vertical Linux boot SMP and cache coherency does not support. Therefore, we are trying to find an alternative way to support SMP in hybrid emulation. Multi-chip support enablement in hybrid emulation. As SoCs become more complex, so it is hard to fabricate them in a single chip. So semiconductor industries are exploring another solutions, and they are moving to the multi-die and multi-chip based chip. And therefore, we are also working on enabling hybrid emulation to support our multi-chip based SoC. Okay, today I read this paper from DVCon 2024, the Unveiling Advanced Hybrid Emulation Methodology for Acceleration Android Home Screen Bring Up and System Level Verification. Thank you for your time. See you next time.